Thank you, Libor, for the introduction and for the invitation. So today I will discuss Magnon spin transport in antiferromagnet from an experimental point of view. So I'm not sure I'll be able really to discuss Magnon topology because from an experimental point of view it's quite difficult, but maybe someone in 40 years will discover that when we discuss that, at the end we discuss Magnon topology like for surface spin wave in the case of ferromagnets. But at least I will try to discuss how important it is to control the Magnon chirality in order to be able to do Magnon spin transport measurements, and especially if you want to detect electrically the transport of Magnons, you need to be really careful at what kind of system you are looking at, look at the chirality, and look at the symmetry breaking, especially in the case of antiferromagnetic system. So in the last years, there were a lot of interest in order to study antiferromagnets for potential spintronic devices for, I would say, three main reasons, which are the following, which are related to the characteristic frequencies of antiferromagnets, which are generally in the terahertz regime and not in the gigahertz regime like for ferromagnets, because antiferromagnets, most of the time, they do not emit any stray field, and because they are quite resilient against external magnetic stray field, which means that at the end, you could expect to develop some ultra-fast, scalable, and robust devices. But the key question then is how can we control the properties of those antiferromagnets? So there were some theoretical predictions that showed initially that one could use spin currents or spin orbit torques in order to try to manipulate electrically antiferromagnets. And so it was based on those predictions that people thought about developing different kinds of devices based on antiferromagnets, such as an antiferromagnetic memory, or an antiferromagnetic transistor, or even potentially an antiferromagnetic oscillator that will oscillate in the terahertz regime. So until now, there have been a lot of studies about this concept of antiferromagnetic memories with various experimental realization, but not so much about those two concepts, because then you need to be able to control not only the static properties of an antiferromagnet, but also their dynamical properties, so you need to be able to manipulate spin wave in an antiferromagnet. So my talk will be more related to some preliminary results that could maybe allow to develop those type of devices. So if one wants to be able to manipulate spin wave in an antiferromagnet, most of the time you have, I would say, at least three key requirements. The first one, and it was said also in the previous talk, is to work with insulating antiferromagnets, because if you want to have magnons with sufficiently large spin lifetime, you need to find a material with quite a low magnetic damping. So for that, you need to work with a magnetic insulator. Also, and I will come back on that point, if you want to have Magnon mode that can carry spin information, you need to find some system in which you have circularly polarized magnons, and I will come back to that. So if you work with a magnetic insulator, and if you want to control electrically the properties of this insulator, you need to use interfacial spin orbit torque. So you also need to find a system in which you have quite a large p-mixing conductance between, for example, an heavy metal that you will put on top of your insulating antiferromagnets. And the last key requirement is probably if you want to trigger some sustained oscillation, you need to find a system in which you have quite a low magnetic anisotropy, so that the threshold current density you need to reach in order to have sustained oscillation is not too large. So we think that maybe we found one of the systems that will fulfill those three requirements. And this system is quite well known at the end in the field of magnetism. It's called Hematite. It's iron oxide. It's also the main component of rust, and it's a system in which was introduced the concept of DMI. So I will come back later to the properties of this system. But what we have been doing using this insulating antiferromagnet is studying the Magnon spin transport using electrical excitation and detection schemes. We have been trying to understand what is the role of Magnon chiralities in the spin transport properties that we have been measuring, the role of symmetry breaking, and lastly, and I will come back to that at the end, how important it is to have large magnetic domain if you want to propagate efficiently spin wave in an antiferromagnet. So hematite, why is it a prototypical antiferromagnet? For one main reason, which is the following. So below what is called the Romain transition of about 260 Kelvin, it's a really classical easy axis antiferromagnet with two sublattices with opposite magnetization. But above it, you have some phase transition at the Morin temperature, and then it's a canted easy plane antiferromagnet. This is due to the fact that you have some DMI field that will induce a small canting between the two sublattices above this Morin transition, so that you have a weak moment. It's an easy plane phase, which means that the spin also can rotate quite easily within this easy plane. So then if you just do, as an experimentalist, some simple squid magnetometry measurements, you can detect this transition by seeing the emergence of this weak moment above 260 Kelvin. So you can easily detect when you are in the easy axis phase and when you are in the canted easy plane phase. It's also quite an interesting compound for the following properties that we measured only recently. So if you just try to do some antiferromagnetic resonance on a single crystal of hematite, you will see this type of curve, so with multiple peaks that are quite difficult to analyze. This is because in a single crystal, generally you have some small defects, so you have some part with different anisotropies, and the uniformity of the field you use for the excitation is not so good. But if you just look at the line width of a single peak, and if you try to extract the magnetic damping in this compound, you will see that it is below 10 to the minus 4, maybe even below 10 to the minus 5. So it is as low as what you could get with the best ferromagnet like yttrium iron garnet. So you have a compound in which the Magnon spin lifetime can be quite large, so you can expect to manipulate the propagation of the spin wave. What is also quite interesting is that if you try to measure what is the size of the antiferromagnetic domain in the single crystal, you will see that they are quite large, generally below above a few hundred micrometer. So that you can propagate a magnons in a single domain. And that's what we have been doing first. So the last key requirement we needed in order to be able to manipulate electrically the properties of magnons in this system was to look at what is happening when we put an heavy metal layers on top of this insulating antiferromagnet. Do we get a good spin mixing conductance? Are we able or not, for example, to detect the direction of the antiferromagnetic order? So the first studies we have been doing is called spinal magnetoresistance measurements. So the idea is the following. So you have your heavy metal stripe, you inject a charge current, you will generate, through the spinal effect, a transverse spin current and a spin accumulation at the interfaces. Then if your system, so if this heavy metal stripe is on top of your antiferromagnet, you can have two configurations. In one case, for example, the Snell order will be parallel to the spin accumulation. So in that case, you can have some spin flip scattering at the interface that will emit a magnons, but also you will have some reflection of this spin current. And this spin current then can be converted again in a charge current through the inverse spinal effect. In the second configuration, in that case, the Snell order is perpendicular to the direction of the spin accumulation, so that the spin current is absorbed in the antiferromagnetic materials, so that you don't have this extra charge current that is generated by the inverse spinal effect. So just by measuring the resistance state in the heavy metal layers, you can expect to detect what is the direction of the antiferromagnetic order in your system. So this is what we have been doing. So in that case, at the applied field, the antiferromagnetic order is parallel to the spin accumulation, and then we just record the resistance in the platinum stripe. What we do first, in order to control the direction of the antiferromagnetic order, we apply a field along the direction of the easy axis. And so when you reach what is called the spin flop field of an antiferromagnet, this Snell order will become perpendicular to the direction of the applied field in order to reduce the Zeeman energy. So that in that case, what you can see in those curves is that at the spin flop field, we observe quite a large increase of resistance, which is due to the fact that above it, this Snell order is perpendicular to the direction of the spin accumulation. So just by measuring this resistance, we can easily detect the spin flop field, and we can extract some crucial information about the anisotropies in this system. We can do those type of measurements for different angle between the easy axis and the direction of the applied field, and so we can record what is the critical field as a function of this angle. So then, from the amplitude of the signal that we were detecting, we can also extract the spin mixing conductance, which is as large as what you would guess with a ferromagnetic insulator, which means that the interaction between the electronic spin current and the local magnetization is as strong in the case of an antiferromagnet as with the ferromagnets. So then if you try to fit those type of curve, and if you do that as a function of temperature, then you can try to model those curves with some simple model based on two sublattices model. And you can extract what is the anisotropy in your system, what is, for example, the DMI field in your system, and this as a function of temperature. So what you have is a surface-sensitive technique that can allow you to extract some interline information about either your single crystal, but also in thin film, which means that you don't need to go to synchrotron-based facilities in order to get information about thin film of antiferromagnets. So I think it's quite a powerful technique. So to conclude on this first part about just the magnetic properties of hematite, so we have an easy axis system or an easy plane system, depending on the temperature at which we are working. In this system, the magnetic damping is really low, and we can control the direction of the antiferromagnetic order with magnetic field of a few Tesla and detect electrically the direction of the antiferromagnetic order. So we have everything, let's say, in order to try to play with the spin wave in the system and try to manipulate them. So then what we have been doing, we have been developing those kind of non-local structures in order to study Magnon propagation in the system. The idea is the following. So again, you will have a platinum stripe on top of your insulating antiferromagnet. You apply a charge current in one of them, so you again have this spin accumulation at the interface. And when you have spin flip scattering at the interface, you can generate a propagating magnons. Then, if you change the distance between the platinum injector and the platinum detectors, you can study the propagation of the spin wave to see how fast the spin wave decay. And you can detect the propagation of the spin wave in the second platinum electrode through Magnon absorption and electrical detection, again, through the inverse spinel effect. So then the first key question we wanted to answer in which phases we should investigate, more the easy axis phase or the easy plane phase of hematite. Because in which case can we really transport spin information? Formation. And so, yeah, we wanted to investigate those three questions. So, yeah, how antiferromagnetic spin wave can carry spin information, how far they can propagate, and what is the role of the antiferromagnetic domain in the Magnon propagation. So if one considers the case of an easy plane antiferromagnet, as it is the case for hematite above the more in transition, but also the case in many compounds that have been studied in the literature, there you will see that if you look at the classical spin wave mode that you have, those modes are linearly polarized, which means that they do not carry spin angular momentum. And maybe from a theoretical point of view, it's not so important, but from an experimental one, if you want to study Magnon propagation and the transport of spin information, you need to find a mode that will be able to carry spin information. So this is not the case of in easy plane antiferromagnets, because in that case, the net spin transport that you will be able to propagate will be equal to 0. So let's say maybe we should focus more on the case of easy axis antiferromagnet and on the easy axis phase of hematite. Because in that case, at the applied field, so we have two energetically degenerated Magnon modes, but those two modes are circularly polarized, which means that they carry spin angular momentum. The main problem is the following, is that those two modes, they carry opposite angular momentum. So if you have the two modes that are propagating at the same time, again, the net spin transport will be equal to 0. So you need to be able to lift the degeneracy of those two Magnon modes in order to have a net spin transport that is not equal to 0. And what is quite interesting is that, again, so if you have a platinum stripe on top of your antiferromagnet, if you apply a charge current, you have this spin accumulation at the interface, and through spin flip scattering, you will be able to tune the Magnon population of the two modes. You will enhance the Magnon population of one mode and decrease the Magnon population of the second mode, depending on the sign of the spin accumulation that you have at the interface. So that you can expect that only one mode will propagate, and then that you will be able to detect the propagation of this mode in the second platinum electrode. And what is quite nice, or at least quite surprising, is that the contribution of the two sublattices will add up in the electrical signal that you will be able to detect through the inverse spinel effect. So based on those considerations, we decided so to pattern those type of non-local structures on top of our single crystal of hematite. So we have a platinum injector, and we have two platinum detectors. So we can, in that case, detect two types of signals. One is related to the one I was describing until now, and I will call it either the first harmonic of our signal or the spin bias signal. it's related to the magnons that you inject through the spin accumulation that you have at the interface. It's an effect that is supposed to be linear as a function of currents. But at the same time, when you apply a charge current in a platinum stripe, you will also have some Joule heating in your system. So you will also generate a thermal gradient. And this thermal gradient can also generate propagating magnons through the spin-Seebeck effect. This effect is quadratic in current, so you can also detect it as a second harmonic of your signal, and I will generally call it the thermal signal or the spin-Seebeck signal in the rest of my talk. So then, what do we observe in the experiment when we do those type of measurements? So initially, we just consider a system where the z-axis is parallel to the platinum stripe at zero applied field, so that it's perpendicular to the spin accumulation at zero field. And then we record the spin bias signal and the spin-Seebeck signal. What is quite interesting to notice is that at low applied field, we do not observe any spin bias signal, and we see only a spin bias signal when we reach the spin flop field, with a maximum of signal at the spin flop field. So it seems that at the spin flop field, Magnon propagation is enhanced, or at least the electrical signature associated to the Magnon propagation is enhanced. And the question was, how can we explain this maximum of signal at the spin flop field and the fact that the signal is non-zero above it and completely zero below it? What was maybe even more surprising is that if we look at the spin-Seebeck signal at the same time, we do not detect any signal, just a small bump, but it's nearly equal to zero. So we wanted to explain those three features. So let's first focus on the spin bias signal. How can we explain this maximum and this non-zero signal above the spin flop field? So this second feature can be explained quite easily. Below the spin flop field, the Néel order is perpendicular to the spin accumulation, which means that we cannot inject spin in the system and we cannot have spin flip scattering at the interface. It's only above the spin flop field that the Néel order is parallel to the spin accumulation, so that we can have this spin flip scattering at the interface and generate a propagating magnons, and that's why the signal is non-zero above the spin flop field. Second feature, why is it really maximum at the spin flop field? For that, we need to come back to the definition of the Magnon modes. So as I was saying, we have two circularly polarized Magnon modes, which are non-degenerated at zero applied field. When we apply a field along the z-axis, we will increase the frequency of one mode, and we will decrease the frequency of the second mode. So that when we are close to the spin flop field, we have a soft mode. The energy gap between the two modes is maximized, which means that the difference of Magnon population between the upper mode and the lower mode is also maximized at the spin flop field. So if you plot the inverse of the gap of the two modes, you will see that you also get this divergence for one of the two modes at the spin flop field. So this is how you can explain that you have this maximum at the spin flop field, because you have a soft mode and because you just increase the energy gap between the two Magnon modes at the spin flop field. Then the second question, the last one, was why we don't observe any spin-Seebeck signal. So for that, what we did was to apply a field, in that case, not parallel to the direction of the z-axis, but perpendicular to it. So in that case, what will happen is, instead of leading to a spin flop field behavior, you will just induce a small counting in your system, like that. So you just create a field-induced magnetization. And as you can see, in this configuration, you do not observe any spin bias signal. This is because the Néel order is perpendicular to the spin accumulation again, but you start seeing a spin-Seebeck signal that is nearly linear as a function of the applied field. And this is related to the fact that when you consider thermal excitation, you do not break the symmetry of the Magnon mode. You do not break the symmetry of the system. You break it only when you consider a spin bias excitation. So you need to break the symmetry of your system, and you break it when you apply a field perpendicular to the direction of the z-axis and when you create this small field-induced counting. So it seems to indicate that in order to have this spin-Seebeck signal, we need to induce a small counting in our system. And this was confirmed also when we put some platinum stripe perpendicular to the first direction. In that case, the Néel order is parallel to the spin accumulation at zero applied field. So we can detect a spin bias signal. Then we apply a field again along the direction of the z-axis, and we will induce the spin flop field. Above the spin flop field, we do not detect any spin bias signal because the Néel order is perpendicular to the direction of the spin accumulation, but we start seeing this spin-Seebeck signal because we have a small counting along the direction of the spin accumulation. So it really indicates that the spin bias signal is really related to spin injection along the direction of the antiferromagnetic order, while the spin Seibel signal is generally, at least in terms of symmetry, related to the field-induced magnetization. So then the last question we wanted to answer is, okay, so we have propagating magnons. We understand that we need to have some kind of symmetry breaking in order to detect them and to excite them. Is a symmetry breaking that is related to electrical excitation or by applying external magnetic field. But what is the properties of those propagating magnons? Do we observe propagation of coherent magnons? Do we observe propagation of diffusive magnons, or maybe even spin superfluid magnons? So for that, what we decided to do is to change the distance between the platinum injector and the platinum detectors, and to measure what is the amplitude of this electrical signal as a function of the distance between those electrodes. So when we do that, this is what we can observe for various configurations. Always a linear decay that is followed by an exponential decay of our signal. And this, you can fit it quite easily by some 1D spin diffusion equation, which then indicate that what we are observing is really the diffusive propagation of magnons. It's also confirmed if we look at the amplitude of the signal as a function of the current that we apply in our platinum stripe. It's quite linear as a function of current. We don't see any threshold, so we are far from exciting coherent magnons in the system, but we just observe the propagation of these diffusive magnons. What is quite interesting to notice is that from this equation, we can extract the spin diffusion length of those magnons, and this spin diffusion length, in this single crystal, was always between 5 and 10 micrometers, depending on the configuration we were looking at, depending on the applied field or the temperature. And this is, again, as large as what you can get with yttrium iron garnet with the best ferromagnets, which means that we can also try to develop Magnon devices based on antiferromagnetic system, and that we can really manipulate them. So to conclude on this first part that we perform on single crystal, so we can propagate diffusive magnons over tens of micrometers. We can also do it at the spin pop field, but also at zero applied field when we are in the right configuration. And it's quite important to have a system in which you have circularly polarized magnons. You want to be able to propagate spin information in an antiferromagnet. We control this propagation through interfacial spin bias and by external magnetic field. But the second question, the last question, if we want to develop some real devices, we need to be able to do that not only with single crystals that are, let's say, about a few micrometers thick and generally even more, a few millimeters thick, but to do it with antiferromagnetic thin film. So this is what we have been trying to do quite recently. So the idea was to go some thin film of hematite by pulse laser deposition on some sapphire substrate. And for 100 nanometer thick thin film, we could observe again this Morin transition by screen magnetometry. And when we do spin transport measurements, again, and it was quite nice to observe that, is that we can observe a signal when the Néel order is parallel to the spin accumulation with no signal when the Néel order is perpendicular to it. And this was done both at low temperature and at room temperature by tuning the position of this Morin transition. What was, however, more surprising is that we could observe two types of situations. One was this one. When we increase the field and decrease the field, we observe non-hysteretic spin transport. And in some other sample, as you can see here, we can observe some hysteretic spin transport. And we were quite surprised by those two curves. So in order to understand them, we went to some synchrotron, and we decided to image what is the properties of this antiferromagnetic thin film. So we did some XMLD PIM measurements, and this is what we could observe. So here, depending on the contrast, you can see what is the projection of the Néel order in those two thin films. And you can see that in one case, the size of the antiferromagnetic domain is of a few microns, can be in some cases even close to 10 microns, while in this second sample, the size of the antiferromagnetic domain is much smaller. And it seems that there is some kind of correlation between the size of the antiferromagnetic domain and the fact that we have non-hysteretic spin transport or not. And what is even more interesting is that if then we just study the amplitude of the signal as a function of the distance between, again, the platinum injector and the platinum detector, this is what we observe. So in the case where we have large magnetic domain, we first observe a linear decay and then an experiential decay, and we can easily fit that again with a 1D spin diffusion model. When we have a multi-domain state, it's completely different. We observe a drastic decrease of the signal at small distances, so it's really difficult to propagate a signal above a few hundred nanometers. And this, we can explain it by the fact that as soon as you have a lot of domains with a quite narrow domain wall or large domain wall, you can have some Magnon scattering at the domain wall. So that depending on the size and the width of those domain walls, you will scatter the low-K Magnons, which means that the propagating signal that we will be able to detect will be much smaller. So it indicates that in antiferromagnetic system, and this is also probably the case in ferromagnetic system, but in ferromagnetic system, it's much easier to control the size of the magnetic domain. You just need to apply generally small external magnetic field. But whenever you have those multi-domain states, you cannot really easily propagate spin wave in the system. So the next point we want to investigate that sometimes we have some multi-domain state, and sometimes we can also observe some topological spin texture in our antiferromagnetic thin film. So those kind of roundish shape, and will be to study the Magnon propagation when you have those kind of solitons. And that will be probably the next work we are going to try to do. So I will conclude my talk on that. So we have seen that we found a system in which we can really try to investigate some of the theoretical prediction concerning Magnon propagation in antiferromagnets. That we have been doing that first in single crystal, but now we are going to our thin film. And if we can go to even thinner film, maybe we'll be able to excite coherent Magnons. Because until now, we have observed mainly, only diffusive transport of Magnons. But the idea will be to go in that direction in order maybe to excite boson-shine condensate in an antiferromagnet. And I thank you for your attention.